In this video, we're going to continue looking at the concept of continuity, but now specifically focus on piecewise functions. And we've discussed this several times, but piecewise functions are not considered elementary functions because they're not formed by using just basic arithmetic operations or composition, right? So the thing is, do we have to do something completely different for them? In fact, no, we don't. All we have to do is to utilize our definition of continuity. And let me remind you of what that is. So f of x is continuous at x equals a if and only if this is true. Well, so 1, f of a exists. 2, the limit as x approaches a of f of x exists. And then finally, these two pieces have to be the same. So the limit as x approaches a of f of x has to be equal to f of a. And in many respects, you can think of this as a continuity checklist, right? So, if I gave you a function and said, at this specific point, is this function continuous or not? Then you would go through and check the function value at that point. Check the limit, two-sided limit at that point, and then check to see if those two things are equal. Now, with the piecewise function, before we can get to the two-sided limit, we normally have to use the one-sided limit. So we might have to split this into the limit as x approaches a from the right, and then the limit as x approaches a from the left, right? So that's really all that we need, right? So we don't need any additional concepts. We just need to now apply our definition of continuity. So the best way to do it is via examples, right? So we're just going to go through some examples, and in each of these, what we're going to discuss is determine all the points, the values of x at which the function is not continuous, right? So we're going to, here are the instructions: find all values of x at which, well, in fact, let's do the positive, at which each function is continuous, right? So each function is continuous. That's the first thing. If there are any discontinuities, classify them as either removable, whole, so removable or a whole, or a jump, or as being an infinite discontinuity. So if applicable, classify each discontinuity, right? So it sounds like a lot to do, but we can accomplish most of it in just a few steps. So if applicable, classify each discontinuity. All right. Okay, so let's go through, and that's what we're going to do for each of these functions. So let's start with and these are all going to be piecewise functions. So let's say we have something like this: x squared minus 1 when x is greater than 1, and then let's say 2x plus 3 when x is less than 1. Right? So let's say let's identify all the values of x at which the function is continuous. Let's do that first. Well, both of these pieces are polynomials, right? They're polynomials. So we know that individually this function or this piece of the function is going to work for all values of x. So in other words, this function is going to be continuous whenever x is greater than 1. And again, this is another polynomial. It's a linear polynomial. And again, we know that polynomials are going to be continuous on their domain. In this case, the domain that's being used or that's applied to this function is x less than 1. So what we realize is if I were to ask you, so the first thing I would check is to see, does f of 1 exist, right? And it doesn't, right? Because there is no equal sign on either inequality. So I wouldn't know which piece to plug it in, right? So f of 1 does not exist. Right? So there is no function value, so we know it can't be continuous at x equals 1, right? So what we can say is now for sure we can say that f of x is continuous when x is less than 1, that's this piece, or when x is greater than 1, but not at 1. So that answers the first part. And again, this was easy because the pieces were polynomial, and we just had to see, okay, what about our continuity checklist? So we checked the function value, and it doesn't exist, right? Now, if we want to classify this discontinuity at x equals 1, if we want to classify it as either a hole or a jump or asymptote, a vertical asymptote or infinite discontinuity, then we would have to check our limits, right? So let's check the one-sided limits to see what happens, right? So let's take the limit as x approaches 1 from the positive side of this function. Well, when x is close to 1, but just a little bit bigger, then we would end up using the top piece of the function. So we would end up having 1 squared minus 1, that's 0. Now let's see what happens from the left, right? So if we take the limit as x approaches 1 from the left of this function, so when x is close to 1 but less than 1, we would use the bottom piece. So we would end up getting 2 times 1 plus 3, that's 5. So because both of these, so two things we can say, both of these are finite. In other words, these are actual numbers. They're not plus or minus infinity, but not equal. That's the definition of a jump discontinuity, right? So in this case, the function, so at x equals 1, f of x has a jump discontinuity, right? And we know that because the two one-sided limits, right? So our limit from the right, our limit from the left, they both exist, but they're not the same. So in fact, if we were to graph this piecewise function and graph it with a window that includes 1, we would see basically this. Well, we might not see exactly what I'm going to show, but we'll see something like this. So here is 1. Let me just make sure I have the pieces right. So when x is less than 1, it will be the linear function. So it's going to look something like this. Well, actually, let me think. Yes. So it's going to look something like this, and then it's going to approach the 5. That's what this is saying, but it's going to be open, right? Because we don't have an equal sign there. And then the other part, which is a parabola, the x squared minus 1, well, it's going to approach 0. So it's going to start down here, and again, it's going to be an open circle, and then it's going to go up like that, right? So this is the graph of this piecewise function, but because f of 1 doesn't exist, there is no shaded in circle at either endpoint or anywhere else that corresponds to x equals 1. But we can see the jump, right? So that answers the two questions for that piecewise function, right? Let's move on and check another one. Okay, so our second example, and again, this one will have two pieces. So this one will be e to the x minus 1, right? So now we have an exponential function there, and this is valid for x greater than or equal to 1. And then here we will have 3 minus 2x when x is strictly less than 1. All right, so there's our function. And again, the two pieces, right? The top piece, which is an exponential function. Again, the bottom piece is another polynomial. It's a linear function. So both of these are continuous for all values of x, right? Again, because we know exponential functions are always continuous. Linear functions are always continuous. The question is, does the piece of the function from the right meet at the same point as the piece of the function from the left, right? So now let's go through our continuity checklist and see if everything works. So first, again, the question is what happens at 1, right? And why are we choosing 1? Well, that's because where the function changes from one piece to the next. So let's start by answering the question f of 1. Now we have an equal sign, so we know which piece of the function to use. So that makes f of 1 well defined. So it will have a function value. Let's see what it actually is. So plugging 1 into the top piece, this is e to the 0, which is equal to 1. Perfect, right? And now let's check the limits. So let's check the one-sided limits to see if those exist. Right, so let's take the limit as x approaches. Let's first do 1 plus, right, of this function. Well, 1 plus, you're still using the top piece because you're close to 1 now and just a little bit bigger, right? And you're getting closer and closer to 1. So we would evaluate the top piece of the function. So that's e to the same 1 minus 1. So it's still equal to 1. So what will happen is if the one-sided limit from the right is also equal to 1, then everything would meet up at that same point, right? So let's see the expectation. Will it work? Let's see. So if we now evaluate the limit as x approaches 1 from the left, a little bit less than 1, so you're on the bottom piece. We can evaluate it. So 3 minus 2 times 1, that's 3 minus 2, that's equal to 1. So whenever all of these numbers are the same, then it means that the function is continuous at that x value. So not only is this piece continuous and this piece continuous, but the entire function altogether is continuous for all real values of x, right? Before I write that down, just to again give you an idea of how the sketch of this would look like. So at 1, so the bottom piece here is a linear function that has a negative slope. So it's going to be decreasing. So it's going to go down and get to, well, actually, let me fix that here. Let's do this. And the y value here that it would correspond to is 1, right? So right here. And then the exponential piece now also starts at 1, but if you think of the basic graph of e to the x, and then you do that translation of 1 unit to the right, so it's going to start here at 1, and then it's just going to go up in that exponential form, right? So you can see that this function, right, a piece of it is linear, a piece of it is exponential, and both pieces meet up at the same point. So the function, it doesn't have any holes, it doesn't have any jumps, it definitely doesn't have any vertical asymptotes, so we can say that this function, so f of x, is continuous on the interval, so the entire real line, right? It might look a little weird with that almost like the sharp corner right here, but that's fine. It's still, you can move along the graph in one continuous motion without having to lift your finger or your pen or your pencil or whatever tool you're using, right? So another way to say this is that f of x has no discontinuities. So then there's nothing to classify. So f of x has no discontinuities, right? And that's an important thing too. I mean, sometimes I know the piecewise functions can be a little strange, but sometimes they behave normally, right? We just have to know how to deal with the separate pieces, all right? Let's look at a third example. And we're pretty much halfway there. I wanted to get 4 examples done. So let's look at number 3. So here's our piecewise function. And I think I'll do one a little bit different now and change the x value that we're going to focus on at instead of making it 1, let's make it something like 0. So it's 1 over x when x is strictly greater than 0, and then it is 1 plus x when x is less than or equal to 0, right? So that's our function. Now let's look at the two pieces. We have a rational function, your simple reciprocal function, 1 over x, and then we have the linear function, 1 plus x. So let's do the same thing. We're going to discuss where is it continuous, and if it doesn't have, if there's a point where it's not continuous, then we will classify the type of discontinuity it has. Again, the polynomial pieces are always fine. This piece, however, is a problem. And it's a problem whenever x gets close to 0, because then you'd have a denominator that's getting very, very small, right? And then when you take the reciprocal, again, the reciprocal of something that's very, very small is something very, very large. So let's go through and figure out what's happening at 0, right? So as far as the function value is concerned, that's okay because the equal sign is on the linear piece of the function, which I can always plug 0 in and get a number. So that one's good. So f of 0 exists. That's good. It's in the domain. So f of 0 exists. Next, let's look at our one-sided limits. So let's start with the limit as x approaches 0 from the left of f of x. Well, when you're less than 0 but close to it, it means you would be again on the bottom piece. So again, it works fine. It's 1 plus 0, that's equal to 1, right? So the function value is 1. The limit as x approaches 0 from the left is 1. Then we would love to see what we saw earlier where the function value and the two one-sided limits were the same. Well, I hate to break it to you, but, well, let's look and see. So now, when we approach 0 from the plus side, right, just a little bit bigger than 0, but getting closer and closer to 0, then that's where the top piece comes in. Because this piece applies when x is positive, but and this is saying we're close to 0 and x is positive. So when I go to evaluate this one-sided limit, I have to use the top piece, and look at what's going to happen. I'm going to have the 1 over 0 plus. Right? And this is that classic form that tells us that we actually have an infinite limit, right? And in fact, the function goes off to positive infinity, right? So what does this one look like? What does this one look like? Well, let's see if we can sketch it. So at 0 now, in addition to just putting that, I have to put the little dotted line to indicate that, yes, because of this fact, because we now have one of our limits that go off to positive infinity, we are, in fact, we have an infinite limit, and we know that infinite limits correspond to vertical asymptotes. All right? So it's just a matter of kind of getting the sketch. So if we do if we graph this bottom piece first, the linear piece, remember it approaches a value of 1, so it's going to go up like this. It has positive slope, and it actually, because of where the equal sign is, it's actually shaded in there because we know f of 0 is 1. So this would correspond to 1 right there on the y-axis. But then it's the other piece of the function where it will go off to positive infinity. And if you remember the graph of 1 over x, you might remember something that looks like that. Right? Not quite as squiggly there, right? But that's the graph of 1 over x, and we have to sketch it for this domain. So you can see that we have an infinite discontinuity. It's not a jump. It's not a hole, right? This piece of the function never stops going up. So it's not a finite jump, and there clearly isn't a hole anywhere. In fact, this function is defined for all real values of x. Right? I can take f of x, and no matter what number you tell me to, I can always plug it into the appropriate piece. The reason why is that when the only problem here is when x is equal to 0, right? But x is equal to 0 is in this domain, so I would use this piece of the function. If x is greater than 0, I can always plug the x values in and get a specific number. The problem is, though, as those numbers get smaller and smaller, like if I put numbers like 0.1, 0.01, 0.001 into this function, when I take the reciprocal, we get large y values, right? So even though it's, we can always find a y for values in this domain, it's the fact that those y values are getting so large that forces the function to have an infinite discontinuity, right? So let's state this. So f of x is continuous, right, on the interval basically where x is less than 0 or greater than 0, but at 0 the function has an infinite discontinuity, right? So at x equals 0, f of x has an infinite discontinuity, right? Okay, so these are a little bit stranger, but we see how they come about. Now for our last example, let's take, again, another piecewise function, and I want to show you another type that sometimes looks a little strange. And then we have, so this is x squared minus 1 over x minus 1. And this is used whenever x is not equal to 1, right? And then when x is equal to 1, it gives a constant value of 3, right? So sometimes you have piecewise functions that look like this, where you use one piece of the function for all but one value of x. And then for that value of x, you have another piece, or sometimes it's a constant value that's used, right? So let's go through and do our continuity checklist. So first, obviously, the value of x that we are concerned about now is 1, right? So f of 1, we wouldn't look at the top piece because we only use that piece whenever x is not equal to 1. So when x is equal to 1, the function value is 3, right? Now, here we don't have to look at the one-sided limits, because on either side, whether you're bigger than 1 or less than 1, you would be in that part of the domain, right? So we don't have to do the one-sided limits because it's the same function whether your x is bigger than 1 or whether it's less than 1. Another way that this condition can be stated, this can be stated as saying you use it whenever x is less than 1 or when x is greater than 1. So since it's the same function, whether we're approaching it from the left or from the right, we just need to compute one limit. So let's take the limit as x approaches 1 of our function here, right? So now this is saying we're getting close to 1 from either direction, so we use the top piece. And let's evaluate this and see what we get. So we have our x squared minus 1 over x minus 1. If I try to use my trick to evaluate it, I get that classic 0 over 0 form, because the limit of the top is 0. The limit of the bottom is also 0. Yep. So we have this indeterminate form, but this is one of our forms where we can factor and reduce. So I'm going to use factoring. The top is a pretty standard factorization, the difference of two squares. So x plus 1 times the quantity x minus 1, and then all over x minus 1. And then we can reduce it, and we've done this several times before. And now we can evaluate the reduced form of this function. So we got the limit as x approaches 1 of the quantity x plus 1. So now we can evaluate it, and what do we get? We get 1 plus 1, which is 2. So look at what happens. The function value exists. The limit exists, but they're not the same. By definition, that is a removable discontinuity, right? So when both of when the function value and the two-sided limit exists, but when they're different, it's like, in fact, this is one where I can graph it. When you graph this particular function, right, at x equals 1, so what happens is, let's see, yep. So you end up getting, you have this linear function, and it approaches 2, right? So the whole is, it corresponds to a y value of 2, and then actual f of 1 is at 3. So it's like just 1 unit above that. So it's right here, right? Right. And it looks a little strange. Why am I drawing a line when this is a rational function? But think about it. This function reduces to x plus 1. That's what happens here, right? So we simplified this, and in fact, it's just a linear function, but it's a linear function with a hole, right? So looking at this graph, we can see that the function is continuous for all values of x except 1. And at 1, the function has a removable discontinuity or a hole. So let's say that. So again, answering the two questions, this function is continuous when x is less than 1 or when x is greater than 1, which again you could simply state when x is not equal to 1. Well, what happens at 1? Well, we figured that out, that at x equals 1, f of x has a removable discontinuity, right? So hopefully these three, I'm sorry, actually 4 examples, right? You got a boatload of examples now, kind of illustrate what you have to go through with the piecewise function, right? You have to check the function value, check the limits, possibly the one-sided limits. Sometimes just a two-sided limit will work if you just have essentially one piece that works for both less than and greater than the x value. And then you compare the function value and limits to see if they all equal the same thing. If they do equal the same thing, then you have a continuous function. If something goes wrong and either the numbers are different, as in this case, or you end up with an infinite limit, or you end up with the one-sided limits that are different, that's how you get the different kinds of discontinuities, right? So definitely review all of continuity. There's a lot of concepts involved, and definitely look at the examples, and hopefully they'll help you grasp this very important concept, right? See you in the next video.